It's a pleasure to present today on behalf of the DRAGEN Bio-IT team. I look forward to this opportunity every few months when we put out these releases. So thank you for joining. While it's been a crazy few months for everybody with the lockdowns and others, things have slowed down in many places. I'm actually happy to say that the DRAGEN team has been working, as before, and has been able to put out this timely release, and with many exciting new features that we will go over in the next 1 hour. We'll breeze through the slides. We have a lot of material to cover, so we'll try to keep some time at the end to address your questions. And if we cannot get to all the questions, we will reach out to you, directly and make sure that everything that you want answered is done. Okay, so let me start with the slides. Here is a quick, I'll move to slide 2. So here is a quick overview of, what are the updates that we have done with 3.6. So as usual, like we do with many of our releases, there are a lot of new features that we have put in this release. And of course, improvements on speed, accuracy, as well as any bug fixes that we have identified and what you have reported as users that we have tried to address in this release. So very excited to talk about the new features first. So at a high level, we have accelerated the Germline and the Somatic small variant calling as part of this new release. And one of the big ways in which we have done this is we have moved the deBrujin graph, which is part of the haplotype caller for the small variant caller onto the FPGA. So that has greatly accelerated, and I have some data to show that. We are introducing a trimming module in DRAGEN now, and as part of that first trimming option, we are introducing the Poly-G trimming capability. With feedback from a lot of our users and customers where, they have been, using the FastQC to, just look at the quality metrics coming out of the sequencer. Sorry, I think the slides jumped. Let's go back to the second slide. So I was talking about the FastQC. So this, again, feedback from our customers, our sequencing cores who really, run the FastQC, but they find that the application is very slow. So we have accelerated that and brought it within the DRAGEN platform. And then we have general improvements to our accuracy for the small variant calling for Germline and Somatic, and then a couple of new features for the CNV pipeline, methylation, and then general improvements to our cohort analysis or a PubGen offering that we have been building since early this year. Okay, so let's go into some details for each of these features. So, this is a big update for us, is bringing in the deBrujin graph, which is now offloaded to the FPGA. So what this does is it reduces the SNV calling runtime in the cloud and on the local servers with the U200 card. So this is something that I want to emphasize is the new hardware upgrades that we have done are limited or are specific to the U200 card. So these are the new cards or the new FPGA cards that we began shipping, I would say, by the early 2019 or end of 2018. So we refer to these as the U200, the cards that were there prior to the U200 were referred to as the Eagle cards. And the reason we can only do this on the U200 cards is just because the size of the FPGA is much larger on those cards, and the Eagle cards don't have enough room to put in additional hardware accelerators. So that's something that you need to keep in mind. And again, the cloud offering already is on a bigger FPGA, so all these updates that we will be presenting today are available for our cloud users. And what this update does is that it lets us offload things to the FPGA, but it also frees up the CPU that we could use for other things, run other things in parallel. So that's a big update that's happened in this release. So here are some benchmarking numbers And again, I'm on slide 5, and just let us know if the slide doesn't refresh on your end, but that's what's live on our end. So as you can see, what we are showing here are a couple of data sets that we have benchmarked against. Something on the webinar that's moving the slides. Okay, I've pushed the slide 5 one more time. Sorry about that. So what we are showing here on slide 5 is the benchmark of a whole human genome at about 38x coverage, and we are comparing the speed from 3.5, which was a previous release, to 3.6. So on the on-site solution, you can see that the speed up is about 33% for this sample to generate VCF and BAM files. And then the speed up is even dramatic in the cloud. And the reason why we are seeing a much bigger, increase in the speed in the cloud is because the cloud is CPU limited. The F1 instances that we use in the cloud are CPU limited. So they run slower when you're doing the analysis with the CPUs. But now that we do not need to use the CPUs for the analysis, especially for the variant calling, you can see it's going upwards of 40% in terms of its speed up. So this is really a big change. And then again, there is a chart showing for GVCF and BAM. So GVCF takes a little bit longer, so the speed up is not that good, but it's still fairly nice. If you look at the on-site, it's a 28% speed up and about little under 40% for the cloud user. So this is really a huge update and a big cost saving, right? We are saving for the cloud users in not only time, but that essentially translates into money that goes back to AWS, right? So this is really a big update that I think should be beneficial to everybody, right? If you're an on-site user, then you will see the speed up. Again, you'll get your results faster. And then again, those improvements start to show up also in the exome, which is on the slide over here. Again, the exome runs much faster, so the speed up will not be as large as the whole genomes. And then the big update also is for the somatic calling. The on-site is not, as I said, CPU limited, and we are running 2 genomes for a tumor normal, as you can see here. But again, going to the cloud for these deep sequenced data, which is at 100x, about 40x, you can see that the increase is very, very large. So overall, really a big update for us. This took us about a year to put in, just because of the amount of validation, verification to ensure that the data that we are putting out matches what was coming out of the CPU, and all the, the development that it takes to, put this kind of a massive change in the FPGA just takes that much amount of time. But really, this one should benefit everything. Okay. Here is just another, set of benchmarking plots that we have, and this once again shows the runtimes that we are getting for various runs that we're doing, right? So we have VCF, GVCF, VCF it's streaming. So when we say streaming, so these are typically the cloud users who stream data from their S3 bucket. And then, when we are enabling all the callers over here, right? So we have VCF, which is basically the small variant calling, CNV, structural variant calling, and expansion hunter. And you can see that with an F1 2x instance, which is the smallest instance with the fewest cores, we are able to run all the callers in under 100 minutes, right? So that's really a big speed up that we are getting because of the offload to the deBrujin graph. Okay, so moving on to the next update. So this is the trimming option that we now have in DRAGEN, and specifically focused for this release to Poly-Gs, and we're looking at other trimming capability that you can build in, basically using this module that we have developed, right? It can, today we have focused on the Poly-Gs, but the module is generic enough that, we could support many kinds of trimming options. So if you're aware, the two-color chemistry, systems sometimes result in some samples where there is, a Poly-G artifact, where really the side effect of that Poly-G is that it results in, systematic mismapping of reads. And what that does is, you have, these Poly-G artifacts getting mapped to, reference G homopolymers. And some of these Poly-Gs that we see come up with high confidence as well. And as a result, you can get either, data that is mismapped, or you can get analysis times that can take much longer than normally they should. So as a result of that, what we have done is we have developed this Poly-G trimming module that identifies those Poly-G artifacts within your sample, and it trims them on the fly. So we have two options. There is a soft trimming mode. So what it does in that mode is it identifies those Poly-G artifacts. It ignores them when it's mapping, but it doesn't change your sample. In the sense, we are not hard trimming those bases out. We are still keeping them in your file. Your BAM will include those, but when we are doing the mapping, they get essentially ignored. So they're in some sense transparent there, so they're present in your sample, but when we do the mapping, they are not there. There is also the hard trimming option, where if you feel that you want to really get rid of those Poly-Gs, then you can enable that option, but that's an option that a customer needs to enable. By default, we have kept the soft trimming option as a default, because we do not want to remove any bases. We do not want to touch the integrity of the sample, essentially. So you get all your bases in there, but we handle the Poly-G artifacts behind the scenes. Of course, when we're doing the Poly-G trimming, we are also putting out a trimmered metrics file, again in a CSV format like we normally do for all our metrics. And again, that gives you a summary of what was the situation with the Poly-Gs in your sample specifically. So again, that file is something that is available, so that you can look at what was done specific to the sample when we did this operation on that sample. And again, you can see here, right? We just have an example here where if you have a sample with Poly-Gs, the aligned coverage peak in the Poly-G region is so large, and that really messes up the mapping. It really takes additional time to do the mapping. But when we run the Poly-G trimming on that sample, then there is no more of that peak anymore. So again, just something that we have heard a number of times from our customers, that this sometimes becomes a problem in some of their samples. So we thought that this would be an ideal candidate for something that we can implement in DRAGEN, speed that trimming process up, and as a result, bring in a trimming option that can be expanded later to do either additional adapter trimming or other features like, some other tools like a Somatic or others do. So, it becomes, an integrated part of the pipeline versus users having to go out of DRAGEN, do the trimming, and then bring the trimmed file back inside, right? Again, just highlighting that we have two options, a soft trimming option and a hard trimming option. The soft trimming option is the one that's enabled by default. Of course, the Poly-G trimmer can be completely disabled as well if you wish to, so that option is also available. Okay. Another big feature that has been requested, again, by customers like you, and again, as you can see, the development that we do is coming from feedback, from what we hear, what our users would like to get, is many in our sequencing core labs who use DRAGEN, who appreciate the fast demucks that happens with the DRAGEN tool, have said that they do a lot of the FastQC analysis offline on the samples, and that takes a long time. So we felt that that's, again, something that could be pulled into DRAGEN as a part of our QC offerings, right? We do QC at various steps in the analysis, at BCL, at mapping, variant calling, but this is something that we felt is well suited to accelerate and bring onto the platform. So that's what we have done. So again, this is the feature that's coming in 3.6. Once again, limited to the cloud and local servers. It's used to, again, perform quick quality checks on your sequencing runs, basically look at the quality of your FastQC files that are being demuxed. It ingests BCL or sequencing data or the FastQC data, and it performs the calculations and generates metrics that are very similar to the FastQC tool, that has been used, for many, many years already. And these metrics are put out in a FastQC metrics CSV file. So we have a CSV file that gets generated, and there are two options in which it works, and I'll talk about that in the next slide. And what we have also done is, by generating these FastQC files, there are two options. Right? One is you can use the FastQC tool that basically plugs into an HTML environment and generates those plots for you. But what we have done is we have also created a fork from the MultiQC environment. So we've realized that many customers or many users use this MultiQC environment for, looking at mapping metrics, variant calling metrics, and others. And so we have developed a fork of that, and I have some details in the upcoming slides. So you can use the MultiQC tools as well and take advantage of the plotting capabilities there to plot, your FastQC data. Okay. And again, there are two options in which you can run DRAGEN FastQC. So one option is you get your FastQC, FastQ files from BCL conversion, and you can run the FastQC on those FastQ files. And you could run it in a FastQC only mode, which means all that we do is generate FastQC metrics for you. But we have the FastQC enabled as part of the mapping option as well. So anytime today in 3.6, if you run mapping, we automatically generate the FastQC metrics for you. So in addition to the mapping metrics that you get, you will also get the FastQC metrics. And these come essentially at no cost in time. So while we are doing the mapping, we are generating these FastQC metrics for you. So again, there are two options. So one is you have a FastQC only option, which you can set to true. But you can also have the option where you can run it as part of your mapping method, as part of your mapping workflow. Okay. So again, as I said, that you have the option to take the CSV file that we have generated, and then plug it into the FastQC tool to get the FastQC metrics that you have normally seen. But again, what we've realized that as we started working on this, that the application for FastQC is very slow. It's unaccelerated. It's a Java application. It doesn't have some of the the quality metrics that like GC content and others, and just extremely slow and maybe not suitable for many users. So what we did, as I'm showing in this slide, is we have extended the MultiQC capability to support the plots that or the metrics that come out of FastQC. So we are showing in this slide deck on how you can install our fork of MultiQC into your local Python environment, and then you can provide the FastQC files that DRAGEN generates, and then get plots in a MultiQC environment. Okay, so here are the two plots that you can get in the MultiQC environment. We're just showing you an example of two plots over here. And again, coming to the speed aspect of it. So as you're totally aware that the DRAGEN aligner is very, very fast. So while you are doing the alignments, you're getting your FastQC metrics. While you can see in this plot, FastQC, which runs individually on read 1 and read 2, itself just takes 60 minutes to run on a node to get these metrics. But with DRAGEN, you can get them with the alignments in about 10 minutes. And if you choose to only run the FastQC files, then it's even faster, right? So, you have this options to do it in both modes. But again, this is something we feel that a lot of our sequencing cores, our customers who run NovaSeq, who have a lot of FastQ data coming out and they want to check the quality, this improvement in speed would be really beneficial for them. Okay, now moving on to, I think, so those are the three new features that we have introduced in 3.6. In the next set of slides, we'll talk about some of the updates and improvements we have done to existing pipelines. So first, we'll talk about the Germline and the Somatic small variant calling improvements. So here is a summary of what we have done for the Germline and small variant calling improvements. And again, the focus in 3.6 has been on the gain for precision. In the previous versions, we had focused a little bit more on the sensitivity side, but here, on 3.6, we focused on precision because that's the feedback that we got, saying that that's something that we felt was a little bit behind and we needed to catch up on. So on the Germline side, what we have done is we have made some changes to our PCR error modeling. And as a result of that, we have a new hard filtering qual threshold for indels. If you remember in the past, we use a single threshold for SNPs and indels for hard filtering, and that's based on the qual. But now we have kind of separated that out to get an optimal F measure based on the improvements we have done. And on the somatic side, we have improved our FRD algorithm. So if you're aware, we have an algorithm called the foreign read detection for improving the overall accuracy. So that has some improvements. We've improved some of the filtering that we do on the somatic data, and we are introducing the capability of ingesting a hotspot VCF for our somatic pipeline. So those are some of the improvements that have happened in this release. And here are some benchmarking data that we are showing here. And here, this slide shows you the accuracy improvements in SNP and indel precision for germline small variant calling. So you can see for whole genomes and whole exomes, our sensitivity for SNPs and indels is staying more or less the same or unchanged. But what we have done is we have reduced the FP plus FN error counts, essentially. And again, that has resulted in a higher precision for us with no loss in sensitivity. And the improvement is seen to be much higher on our exomes. As you can see, the indel exomes especially, there is almost a 10% reduction in the FP plus FN count. And if you see the bar charts over here, we have looked at about 8 data sets for exomes, and we are plotting on the left side the indel FP plus FN, or the total error count, and you can see that from going from 3.5 to 3.6, almost across all the samples we have reduction, except there's one outlier here. And then the indel sensitivity is staying more or less the same. So I think this one, is an overall improvement, to the indel precision that we were targeting for this release. In moving on to the somatic whole genome tumor normal small variant calling, again, what we are seeing is an improvement in SNP and indel precision. So here you can see the whole genome data where, again, the sensitivity is more or less staying the same. There's slight degradation, but then if you flip from the other side, the precision has greatly improved. And again, this higher indel precision was achieved by some improvements that we have done on the PCR error model, as well as the foreign read detection algorithms, and some improvements in the filtering that we do downstream. Here is a large set of samples that we have looked at for whole genome tumor normal data. And again, these are some of the publicly available samples as well. There are these NYGC cell lines that we have used as well. And you can see in blue that the bars that you see are the precision gains, and then in orange are the sensitivity gains. So the sensitivity gains more or less stay flat. But across this cohort of samples that we are looking at, there are improvements in SNP and indel precisions throughout this the set of samples that we have. Okay. We also wanted to look at how DRAGEN performs with these updates on the NYGC cancer cell lines, right? So these are typically the 3 samples that we use, and which are commonly used, I think, in the industry as well for benchmarking. So this is the 1187, 1143, and the Colo 829 samples. And we're using these because there is some truth set available for these cell lines, right? And there is some high confidence truth sets, you can we've given some metrics over here, regarding the truth set and, the SNPs and the indels in these truth sets. And so we're looking at that and seeing how we are performing with 3.6. What we have also realized as part of this exercise to, look at the data is that some of these data sets lack, they have incomplete truth sets. So what we are doing in Illumina to, get some better benchmarking is we are creating this normal paired data sets. And again, these normal paired data sets, are matching the same sequencing instrument, library preps, and the coverage of the original tumor normal pair. And what that leads us to is it creates this concept of a combo, ROC plot, where we are using the normal analysis for FP counting. So any pass that we see as a somatic call in a normal analysis, is counted as a false positive. And then when we go to the tumor normal, any call that we miss in that analysis counts as a false negative, right? So just because the truth set is still, being curated or it's incomplete, or there is just a lack of high confidence bed, we come up with this kind of a combo ROC to assess, how we are doing in terms of the accuracy. And then based on that, here are some, benchmarking that we have done. And the green plot is GATK4 plus Mutek. The orange is Strelka. And then the light blue and the dark blues are going from the previous version of DRAGEN to the new version of DRAGEN. And then what we are looking at is FP plus FN. So the bars are split into, those two colors. And you can see that, this slide is for the SNPs. The total FP plus FN count, is lower in 3.6. And then that, on the other side, translates into higher precision and higher sensitivity. There is one result over here, which is the SNP sensitivity for the 1143 cell line, where there's a little bit of a drop in the DRAGEN sensitivity compared to GTK. And then we are addressing that. We're trying to see how we can bring that up. But if you go to the next slide, we can see that there's a trade-off where, the indel sensitivity is still much better across the board. So we are trying to address where we can get that right balance. But overall, if you look at all the three cell lines for 3.6, for SNPs and indels, we can see that with 3.6, compared to the previous version, compared to GTK and Strelka, we are getting much improved precision and sensitivity. Okay. And then here is just a note on the option to have a somatic hotspot VCF file. So again, this is a hotspot VCF file that has prior information, regarding the positions or the risk of genetic mutations that you might be interested in, and then that helps with the SNP caller sensitivity, and with almost no impact really to the specificity. So this is an option that is available in this release, and if you see at the bottom here, we show you the command line options, which says the VC somatic hotspots, where you can ingest or we can input a VCF file. Okay, moving on to the CNV updates. So the big update that we have done for CNV calling is we have kind of centralized our segmentation algorithm in some sense. We have, if you remember in the past, we used to offer three algorithms. One was the FPOP, then we had SLM for whole genomes, and then we used to use CDS for the exomes. So what we have done in this release is we have kind of stopped supporting FPOP just due to many reasons. One is that's third party. It was difficult to update. It had many challenges to maintain it, well, and to keep the quality of the algorithm. So while we understand that the FPOP, had high sensitivity, but also that came at a cost where the false positive rate was very, very high on that one. So what we have done is we have kind of centralized everything around the SLM segmentation algorithm, and we're using an adaptive SLM for somatic samples and a heterogeneous SLM for the exomes. We are still keeping the CBS segmentation algorithms, but that's an optional one, so that's something that customers will have to enable specifically. The ones that I'm showing here are the default ones. And then in general, for the updates that we have done to the somatic piece of whole genome CNV calling is there are speed improvements. There are improvements to the purity and the ploidy model. And again, these are really addressing some of the quiet tumors, as we call it, that have been difficult to, call previously, just because, we didn't have that enough sensitivity. So there's some model improvements to help that. The segmentation improvements, which is what I mentioned above. And then we have a new mode called the Germline aware mode. So we have a capability to ingest the Germline CNV VCF file. So if you have a tumor normal pair that you're going to call CNVs on, in addition to the VCF BAP file that we, had the capability to input in 3.5, in 3.6, you also have the capability to input a CNV Germline VCF file as well. So here are some, runtime improvements that we have, seen. So this is again using the 1187 cell line, and just showing you the comparison. The 3.6 is faster for this cell line versus 3.5. So if you're using, whole genomes to do CNV somatic calling, then you should see a speed up in this release. Here is, just some more information on what we mean by, we have improved the purity and the ploidy modeling. Again, in 3.5, we have identified areas where, we are seeing, difficulty in calling some of these, low tumors, or low to few CNVs, as you might say, or quiet tumors in these kinds of samples. So here you can see in red that, what we couldn't see in 3.5 before, on the left is a 3.5 plot and on the right is 3.6. We are now able to catch some of those CNV calls that were missed before. Here is a slide showing you the difference between the SLM and the adaptive SLM. So the SLM on the left, again, this is, the important thing is that the plot on the top. And you can see what the adaptive SLM does is for the same data, it smooths the segments essentially, right? The scattering that you can see, or the noise that you can see on the left plot on the top, is really cleaned up in this adaptive SLM. So just we have better estimate of noise, reduction in some of these spurious segments, and that really is beneficial for, maybe more noisier tumor normal samples that, we have seen or experienced in our analysis. So we feel that, using this adaptive SLM mode is, going to benefit some of that, analysis for the whole genome tumor normal data. Here is that option that I mentioned earlier about. So, if you remember in the previous version, we had the option to input the tumor BAF file, which I show at the bottom, but now, you can get a CNV VCF file from the germline sample and then input that into the CNV calling for the somatic analysis. And that should help, get some additional improvements in the CNV calling. Okay. On the RNA side, this is a slide that I have used in the past as well. This is just showing you our internal benchmarking cohort, right? So we have about 153 samples that we use for bulk RNA benchmarking, and as part of those samples which we have collected from various sources, internal and external, there are about 223 fusions that we look at. So just there are incremental improvements that we have made on the RNA fusion caller, and we've shown here comparison. If you look at the green, which is 3.5, in 3.6 on that same cohort, we are missing fewer fusions, and we are calling fewer additional fusions, which means we have a lower false positive rate. So just incremental improvements on the RNA fusion calling in this release. So something that, if you're running RNA fusion calling, you will see some of that show up as well. Okay. We have some updates on the cohort analysis. So this is something that we've been working on since early this year on improving the overall, PopGen sort of offering, or a cohort, large-scale cohort offering. And this first slide that I have is just showing you the workflow related to that, right? So, you generate your GVCF files, from your small variant calling. And then we've kind of sort of split that into two parts where you can use DRAGEN, to speed up this analysis, which is done, now even much faster with the FPGA offload. And then we now have a software-only offering that can do the large-scale cohort calling, right? And it's broken down into two steps here, where you have a GVCF genotyper, which basically, creates your variants, which are genotyped across all the cohort members, so basically columns per sample. And this is something that could be directly used for, GWAS studies, or you can input them into HALE or others. And then, and many of our customers just feel, comfortable to stop at this point. The data that we put out as a multi-sample VCF is sufficient for their GWAS studies, right? But then there are some who want to go one step further, where they want to run the joint genotyping on that. So that's the second step, where again, there is some work being done around, does the joint genotyping across cohorts improve, the genotyping for low frequency calls, essentially, right? For high frequency or the high coverage regions, what we've realized is that there is sometimes none or even worse scenarios where, you can see that the calls get worse as you start to genotype across a large cohort for the high confidence regions, because, if you have enough coverage, the calls that you get in that region are good enough. But what we have seen is that if you are trying to use this in areas of low coverage, then there is benefit to doing that. So again, the update that we have done now in this release for the GVCF genotyper is we can input GVCS from GATK. So if you have generated GVCFs from 4.1 version and above, that's what we have tested, then you can input them into DRAGEN and do the GVCF genotyping. We have also improved the speed of runtime for the joint genotyping, so we are seeing about 3 times faster runtimes. This offering that we are calling for this cohort analysis is a software solution, and we have 2 ways in which we deploy that solution. So if you have a smaller cohort, you can run it on the DRAGEN server in-house. But if you have a very large cohort, then the DRAGEN Box, which is a single node, becomes not very suitable to do that kind of analysis. So we are offering a software solution. This is today available on request for DRAGEN customers, and it can run in 2 ways. It can run on our cloud offering, which is the Illumina Analytics platform. So this is available today as an early evaluation solution. And the software solution is also suitable for running on your local HPC. So you can run it in the cloud using our IAP offering, where we have sort of optimized some of the workflow related to this, or you can deploy it on your HPC. Here is just some benchmarking that we have. So I think the important thing in this benchmarking is to look at the plot on the right, where the joint genotyping has dramatically improved. So we have like 10,000 small panels that we are showing here as a first plot. We have some 160 exome samples that we are running, but we can also see that if you're running the Polaris 150 whole genome samples, the joint genotyping has reduced by almost 75% in this. So again, big improvements. Again, just optimizations to code, parallelism, threading that we do, and other things that are giving us some of these gains versus any other things. Again, this one is showing on if you're running this kind of cohorts on a cloud on our Illumina Analytics platform environment, then for 1,000 samples, if you are running the GVCF genotyping and the joint genotyping, we're able to do that analysis very, very quickly. you can see here it's within a couple of hours. And if you are running 5,000 samples, we are looking at about 50 hours. If you look at the two steps, which is the GVCF genotyping and joint genotyping, to run this. And as we are in the process of completing some of the work for the 10,000 samples. So we are, as part of this release, we are looking at about supporting 10,000 samples in a cohort, but the goal is to getting into much larger cohorts as these PubGen initiatives start to expand all over the world. Okay. Again, I'm just through some of these are just general QC updates. I'll talk about, and you have an opportunity to look at these slides. But the two major updates that we did as part of DRAGEN 3.6 is coming again from some feedback from one of our larger customers. Is we were double counting some of the overlapping bases as part of the QC metrics. So now we have an option called QC coverage ignore overlaps, and then when that's set to true, then we will not do that. We will ignore the overlapping bases as part of our QC metrics coverage calculations, and also we were ignoring the soft clip bases as part of the coverage calculation. So now there's an option where you can include the soft clip bases as well. So these are really the two major QC related updates that we have made. And again, this is coming to align with some of the metrics that some of our JTK customers have been using in the past, and they have been transitioning to DRAGEN, and they fed back that to us. Okay. We have some methylation updates, which we don't do too often, but I think we are getting some resources to work on the methylation pipeline. So what we have introduced in this release is support for TAPS. So TAPS is a new assay that we have seen that's gaining popularity over the traditional bisulfite sequencing protocol. And really the reason why we are seeing some excitement around this assay, and we feel that this is something that will pick up, and we're kind of early in the game, but we wanted to provide some support for something that customers can take advantage of. But really what this assay does is it preserves some genomic complexity because it uses less destructive chemicals. So the sample quality is not degraded as it gets done with the bisulfite sequencing. And what that enables us to do is it enables us to use lower input DNA, the complexity or the genomic quality is preserved of the sample. It reduces the mismapping rates, and at the same time it becomes suitable for analysis for liquid tumors or ctDNA kind of applications. So that's where we see that this assay can gain a lot of traction, and we have now built in support for analysis of this assay, and it's done by a simple command line that you can enable called methylation TAPS. So if you're using a TAPS methylation assay, or if you are intending to go there, there is support that is now available in DRAGEN, and in the next version, we are going to do some more work on methylation. So I'm really excited. This is something that has been lagging in our offering for a while, but we now have some, push and some resources that can work and improve this offering. So really excited about, this thing. At the same time, we are looking at some, inefficiencies, in our, outputs that we are putting out. So the cytosine report that was previously being put out had a lot of zero coverage files or zero coverage regions that were being reported, and that resulted in a very large file size. Also, it impacted the runtime. We have kind of optimized that now. We don't report those zero coverage regions. The file sizes are much smaller. The analysis is much faster, right? So just some cleanup that was, due for a while, I think, in this pipeline. And we've also reviewed and gone back to, some of the alignment settings that we had for the methylation pipeline. And we have, brought in some of these alignments, settings to now be more concordant with Bismarck. So, we've put a table over here, something that, you can look up and see if these settings that you've been using, if it's better to go to the newer ones because they match closer to Bismarck. Of course, there's support to go back to the older settings if you wish to, if that's something that you've been comfortably using before. Just some, couple of updates to the BCL conversion. So if you're using DRAGEN today to do the hardware accelerated BCL conversion, we have a new feature called minimum adapter overlap. So this is really regarding, the case where, you have a last base that sometimes gets, trimmed or clipped. And again, the skew is, possibly a 25% chance, right? Because, one of the four gets trimmed at the end. So this was something that was fed back to us by one of our customers, that they wanted that option to keep that last base and not trim it. And so we have a setting now that will prevent that from happening. And at the same time, there's another update that we have made is where you have a column that you can add to your sample sheet called sample project. And what that does is it will let you dump FastQs for set of samples or a particular sample into a specific project in your BCL folder. So now you can organize your samples based on samples that are related to a specific project versus all the FastQ files being dumped into one single folder, right? So if you are taking samples for, from different, of your customers, who want the data returned back, you can break them down into different projects, so it's easier to manage. Again, we have done some, code fixes, some stability improvements, and some better tolerance for some of the corrupted data that might have, sometimes crept into, our flow cell files. So, just some better tolerance so that we don't throw errors. There would be warnings, but we'll go and process your, demux your flow cell to get you the FastQ file. So just some of the issues were reported by some customers. So, we've been able to address that, and they've been successfully able to, demux their flow cells after those changes. In terms of the BaseSpace updates, so if you're a BaseSpace user, if you use some of our apps on BaseSpace, the apps for 3.6 will come only in mid of July. And again, just it's not that we are behind, it's just that our BaseSpace team has been, working very hard on the COVID applications. So, we have the RNA pathogen app, the metagenomics BaseSpace DRAGEN apps. So those are some of the apps that they have been supporting building over the last few months. And as a result of that, they are catching up on, updating the 3.6. So we're a little bit behind, but, we're there. We're almost there. In about a couple of weeks, we should see these updates. And what will happen as part of that update is, improvements or updates, to the existing apps that we have, but also we are bringing in the new MultiQC app, right? So the MultiQC feature that's in 3.6 will be made into an app, and just general updates to our, Germline, joint calling, and methylation apps as part of this update. And again, the 3.6 version for the on-site users is available today on our website. So if you go to the website, to the DRAGEN support page, the installer for the on-site version already exists. Once again, the BaseSpace apps are coming mid-July. And then for us, the AWS Marketplace is one of the places where we push DRAGEN to. That update will be coming in the next week or two for 3.6. So once again, I think I'm on the last slide now, just iterating, that the hardware updates are specific to the U200 boards, which are, some of the newer boards, that we've been shipping for the last 18 months or so. And also it's available in the cloud. So all the cloud users, they can take advantage of the speed up and some of these new features. There is a general update on the runtime for structural variants. So there is a speed up of about 20% if you're using, the GRCH38 alt-aware reference. So, any analysis done for structural variants is sped up there. And then another update that we have done is we're putting out this Ploidy VCF file. So basically, we have a Ploidy caller that is now, across the entire genome. And so we're reporting the whole chromosome mosaicism, including the trisomies. and it's now output as a standard VCF file that you can look up. So it's a file that is per chromosome, and you can see, like, in this example that we are showing here, right? It's the coverage is 2x for the whole, for the diploid human sample here, but there is a trisomy that you can see here in this chromosome 12. So this is something that we have put out as a separate VCF file that you should automatically see when you run, our pipeline. So that's something that you will see as a new feature. So I think that's the end. So I think I'm out of breath. A lot of changes, a lot of updates, some very exciting ones. So I'm hoping that, you all get a chance to use this new release, and, we are available as always to hear, what you like, what other improvements we can make. And then we have